Okay. Yes. Ah, 2006, sorry. 306. Mistake. CSC 306. Engineering analysis 2. Yeah. So pay attention. We want to be looking at what we call ODE. ODE. This is where we are starting from. ODE. What do we call ODE? Pay attention. You know that normally in a differential equation or in an equation, we usually have what we call dependent variable, and also we have what we call independent variable. For example, if I say y is equals to f of x, if I say y equal to f of x, you see this y that is there, it is called dependent variable. It's called what? Dependent variable. And this x that is there is called independent variable. Yes. Whatever x, you see, whatever x is will determine the value of y. So y is dependent and what? X is independent what variable. Now, what do we now call ordinary differential equation? Now, pay attention. What do we call ordinary differential equation? You see, for ODE, the unknown function depends on only one independent variable. One independent what? Variable. Now pay attention to something. You see, in a nutshell, whenever you hear about ordinary differential equation, we only have what? One dependent variable, one independent variable. Let me give you an example. If I say x squared d square y over dx squared plus x dy dx, let me say plus x squared minus 4y equal to 0. Look at this type of equation now. If you observe, you see, you're having something like dy dx. You see, this is this thing like this, dy dx. You see this y you have at the top is the dependent variable. Whatever you have at the top here is dependent. Whatever you have here is what? Independent. So with what you're having here now, you will see that I'm having just one dependent variable and one independent variable. Our y is the dependent variable. Our x is the independent variable. So if you see them as 1, 1, then we call this an ordinary differential equation. Ordinary differential equation. Yeah. So you see, this is the first type of differential equation we have, ordinary. There's another one again. We call it partial differential equation, PDE. Partial differential equation, PDE. Now look at it. In PDE, the unknown function PDE, the unknown function depends on two or more. The unknown function depends on two or more what? Independent variable. Now, I will explain this on independent variable. I will explain this independent what? Variable. Now, let's explain this. Remember I told you for ODE, you see this unknown function y. You see this function y. Are you there? Is depending only on x. But, yes, but if you see this partial differential equation, the unknown function y will depend on more than one independent variable. You see here, they depend only on one. Now, let me give you an example. So it will be clear. See, and if you see this sign, you know it's partial, del. Now, del 4u over del x is to power 4, you will see plus x del 4u over del x squared del y squared plus del 4u over del y to the power of 4 equal to 0. You see what you have here like this now. If you observe, our dependent variable u, you see, is not only depending on x now, it's depending on two variables. It's depending on what? X and y. Have you seen it? Depending on x, depending on y. For the ordinary differential equation, the unknown function y depends only on x. That is one dependent variable, one independent variable. But for partial differential equation, you have one dependent variable and you have two or more independent variable. Like for example, here now, the dependent variable, if you observe here, it is u. Why the independent variable? Why the independent variable here is what? X and y. Please, do you understand the difference now?
Yes.
Exactly. And also, you will be using this sign del. Hello, sorry. You'll be using this sign del for partial. You only use this sign del for partial. Nice. So let's move on. Just focus. Now, also, you want to learn how to find order and degree. Order and what? And degree of a differential equation. You want to learn the order and degree of a differential equation. You want to learn the order and the degree of a differential equation. Now, you want to find the order and degree of a differential equation. Look. Okay, let's go. Now, how do we get the order of a differential equation? You see, the order of a differential equation is the what? Let's look at what we call order. Order is the highest. Order is the highest derivative present in a differential equation. If you look at order, order is the what? Highest derivative present in a differential equation. Let me give you an example. Look at this question. Look at this. S squared d square y over dx squared plus x dy dx plus s squared minus 4y equal to 0. If you observe, the highest derivative I'm having here is this d square y over dx squared. This is the highest derivative I'm having here. Now, if you observe, the highest derivative I'm having here is to the second order. Therefore, the order of this differential equation is equal to 2. The order of this differential equation is equal to 2. That's how you know. Hello, is that clear?
Yes, very clear.
Exactly. Okay, look at this one now. It could be tricky. Just observe. X dy dx to the power of 4 plus d cube y over dx cube equal to 0. Look at this. If I ask you what is the order of this, what will you tell me?
The order is 3.
The order is 3 exactly. Because you see, don't be tricked by this 4.
Yes.
That 4 is not the order. Just observe what is the order of this one like this now is just order 1. Yeah. So the highest order I'm having here is 3. Therefore, the order is 3. Aha. Now that's highest derivative is the order of a differential equation. Now, what's now the degree? Now, the degree is the power of the highest derivative. Power of the highest derivative. Yeah. Power of the highest derivative. You see, there are some times whereby you can get this. You see, there are some times that you can get this degree directly. Why there are some times that you can get it indirectly. Let me give you an example. Look at this first one like this now. Look at this first one. X squared d square y over dx squared plus x dy dx plus x squared minus 4y equal to 0. Now, can you tell me what is the degree of this differential equation? Now, first thing you ask yourself, what is the highest power and what's the highest order? This is the highest order. This is the highest order. Since you have gotten the highest order, tell yourself what is the power of the highest order. It is having power 1. You see, to get order and degree, you are only concerned with the highest order. To get the degree, just look at the highest order. Then look at the power on the highest order. It's power 1. Therefore, our degree here is 1. If you look at this second one I gave you, x dy dx to the power of 4 plus d cube y over the s cube equal to 0. Our highest order here is 3 and is having a power of 1. Therefore, our degree is equal to 1. Is equal to 1. Now, let us look at this one. Tell me the degree of this differential equation. D square y over the s square all square plus 6 dy dx all cube equal to 1. Now, tell me, what is the degree of this differential equation? What's the degree? The degree is what? 2, exactly.
The
Because
degree of this is 2.
it's 2, yeah, because
the order is
highest
2.
order, the power on the highest order, this is exactly. So the degree is 2. Now, let's look at an example whereby the degree will be gotten indirectly. Look at this one. Look at this one. I have d square y over the x square 2 over 3 equal 2 plus 3 dy dx. How do we get the degree here? Now, this is what you will do. Firstly, let's simplify this power that we have here. Let's simplify this power that we have here. Can we simplify? Let's simplify this power that we have here. Firstly, do you know how to simplify that power?
The only way I'm thinking of is using.
This is what you will do to simplify that power. Let us remove this over 3 that is here by multiplying both power by 3. See, let me multiply both power by 3. Then multiply both powers by 3. What we observe here, you see that you'll be having d square y over the s square. Now the 3 will cancel out each other. You have 2 equal 2 plus 3 dy dx. Then all to the power of 3. Consider what you have made all the power now integer. Like you're not making something like a fraction here. I've cleared this fraction away. Then look at what I'm having now. So normally our order here is equals to 2. And what's our degree? Our degree here is what? Degree is also 2. Yeah. Yeah, that is it. That is it. That's it. That's it. Yeah, that is it. Okay, let's move on to the next step. Now, the next one is we want to look at hold on. I'm coming. Okay. Okay, let us look at how do we know a linear differential equation? A linear differential equation. How do we know a linear differential equation? Yeah, and how do we know homogeneous differential equation? Let's look at linear differential equation. You see a linear differential equation, it has this form. A(n) of x, the ny over the xa plus a(n minus 1x, the n minus 1 y over the xn minus 1 plus dot 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 plus a1 of x dy dx plus a naught of x y equal to f of x. Now, you see, how do you know that what this is a linear differential equation? Number one is that you see, Number one is that you see this function, to know that it's a linear differential equation, you see this function f of x that is there. You see this f of x. This f of x depends solely, that it depends only on variable x. Okay, for this to be a linear differential equation, you see this f of x must depend on variable x. It must not depend on y. It must depend only on what?
Variable x.
Yes, only variable x. That's the first thing. All together. And again, this your coefficient an of 1 like that. Let me just name all of them. Ai of x. That is your I is from something like, I'll explain this. Like your I is something like 0, 1, 2, up to any number that you have there. That is, these numbers that you're having here, we have them like okay, you see this one that is there now. If I say I equals 0, 1, 2, 3, A naught, A1 of x, A2 of x, A3 of x, and so on like that. What I'm saying is that you see everything that you're having here now, they are also what? Functions of x. They are also what?
Functions of x.
Yeah. Let me help you summarize that too. I'm coming. That is all your A1 of x. That is all your AI of x. That is, this AI of x now is representing everything you are having here. They also depend on x. They also depend only on variable x. Yeah, they must not depend on y. It means that if you go and have any differential equation whereby maybe you're not going to have product of x and y like this, then the equation is non-linear. Are we together? It must, all this stuff must depend on x. Yeah, they must depend on x. Is that clear?
Yes.
Yes, exactly. Yeah, and also check again. It's possible for all these coefficients here to be a constant. That you hear something like linear differential equation with constant coefficient. There's no one like this coefficient also, it can be a constant. Yeah, it can be a constant. So if it's a constant, we are saying okay, this is a linear differential equation with a constant coefficient. If it's not a constant, we can say a variable coefficient, and so on like that. So that's that. So let us look at what we call homogeneous differential equation. Homogeneous differential equation, homogeneous DE, homogeneous differential equation. What do you call homogeneous differential equation? Okay, if I have a differential equation like this, let me say dy dx equal to f of s comma y. Now observe this one. If you have a differential equation of this form like this, are you there? Now, how do we know if this is homogeneous? Now, pay attention. You see this thing, this equation is homogeneous. This equation is homogeneous if f of, let me say, ks comma ky is equal to f of s comma y. If f of k comma y, f of kx comma ky equal to what? F of x comma y. Then we can say that what? We can say that yes, this is homogeneous. Yeah, obviously, don't worry. Yeah. Okay, let me show you something. Let me give you an example. Let's see if this is homogeneous. Determine if this is homogeneous. Dy dx equal, let me say, wait, let me say if this is equal to k to the power of, let me say some power m. Let me tell you what I mean by this. Let me say what you're having here is 4x plus 3y. Is this equation homogeneous? Let's check if this equation is homogeneous. Observe. Now, let me call, if I want to check if it is homogeneous, you say, okay, let your f of s comma y be equal to 4x plus 3y. I want to check if this one is homogeneous. So f of x comma y equal 4x plus 3y. Then, now check what is f of kx comma ky. Now, what does this mean? Anywhere you see x, put kx. Anywhere you see y, put ky. So what will be having? 4kx plus 3ky. And you observe from here, I can factorize this k, yes or yes?
Yes.
Aha. K, 4x plus 3y. You can see f of x, now check me. F of kx comma ky is equal to k raised to some power, k raised power 1. You can see that, see, in a nutshell, to know if something is homogeneous, if you can factorize out this k, therefore it is homogeneous. In what order? It is homogeneous in order 1. It is homogeneous in what? Order 1. It is homogeneous in order 1. Yeah. If it's possible for you to factorize that k, aha, then it is homogeneous. But if you see that the k cannot be factorized out. For example, now look at this one. If I give you something like this, I give you something like this. Dy dx equal to, I'm coming, please. Now let's continue. Now let's see, look at this one now. Let's say this one is homogeneous. Okay, let me say equal 4x plus sine y. Is this homogeneous? Okay, let's check. F of x comma y is equal to 4x plus sine y. We want to check if this is homogeneous. Okay, now let's see. Now we have f of kx comma ky is equal to 4kx plus sine ky. Now, which miracle can we use to factorize k out? K cannot factorize, so this one is not homogeneous. Not homogeneous. Don't mistakenly say cos. Let me say you have something like cos kx. Know that it is not equal to k cos x. This is not possible. This is not possible. You can't do something like this. Yeah, so this k cannot come outside. This k cannot come outside. Yeah. So now we want to look at, after you have learned this, we want to look, all these are like introductions. Very important introductions. Now, the next thing we want to look at is this. Check if we want to look at what we call linear dependence. Linear dependence. Linear dependence. Yeah. Linear dependence. Okay. Yeah, there are several definitions to linear dependence, but I want to teach you the idea of the Wronskian method. You want to learn how to know if two solutions are linearly dependent on each other or not using the Wronskian method. Now, pay attention to me very well. Let me say I have two functions. Let me say I have two functions, u1 of x and u2 of x. Now, how will you know if these two functions are linearly dependent? Firstly, you find their Wronskian. How do you get the Wronskian? The Wronskian of u1, u2 is what? You see, it is a determinant matrix. Pay attention. How will you know the order of the determinant that you want to draw? I want to check if they are linearly dependent. These are the two functions. Are they linearly dependent on each other? Because they are two, I'm drawing 2 by 2 determinants. Okay, so this one is u1, this one is u2. u1 prime derivative, u2 prime derivative. Then you find the determinant. Remember, you can find the determinant u1, u2 prime. minus u1 prime
Yeah.
u. Yeah, you can find determinant, I'm sure.
I want to ask, what
Okay,
if
ask question.
we have three functions?
Three, yeah. Oh, yeah, let us
The
look at three
matrix
functions.
going to be okay.
Yeah, look at it now. Let me say we have three functions now. For look at the other ones. Now look at these two functions. For three functions, let me say u1, u2, u3. Now, if I want to find the Wronskian of u1, u2, u3, what do? I will draw a 3 by 3 determinant. Is to follow that pattern. You see u1, u2, u3. The second line will be u1 prime, u2 prime, u3 prime. Why the third one was u1 prime prime, u2 prime prime, u3 prime prime. Now check. Now this is the Wronskian of these three functions. Are we together?
Yes.
Good. Now, if the Wronskian is equal to 0, what do you say? Therefore, the functions are linearly dependent on each other. So what do we say if the Wronskian is not 0? If the Wronskian is not 0, therefore what do we say? The functions are what? Linearly what?
Non-dependent.
Yeah, linearly independent.
Independent.
Yeah, linearly independent. Okay, let us take some example. Let's take some example. Don't worry, I will send this video and this note to you. I'll send the video. I will edit it and I can just put it on my YouTube. I will send the link to you. You can just watch it there.
Right.
And also the notes will be sent to you. Yeah. So now let's go. So we want to show that y1 equal exponential x, y2 equal exponential 2x, y3 equal exponential 3x are linearly independent. That is, we want to ascertain that this Wronskian is not 0. That linearly independent. That's the condition. Okay, let's go. Don't forget solution. To know, we have to use the Wronskian. We have to use the what? We have to use the Wronskian. Yeah. So what's that Wronskian? Wronskian of that function is what? Determinant of y1, y2, y3. Next on derivative, y prime, y2 prime, y3 prime, y1 prime prime, y2 prime prime, y3 prime prime. Now don't forget this. Take note of this trick. If I want to differentiate an exponential function, okay, just bring down this number m exponential mx. The number you have there, or if you differentiate what you have here, you have m, put it here, then write mx.
Yes.
Good. Let us particularize it here. ddx exponential 3x. Don't differentiate 3x. So that's how I'll give you a 3. Then repeat the exponential 3x. That will be the derivative. Okay. So it's just drop down the number. Okay, let's go. The Wronskian is equals to now what's y1? Y1 is exponential x. Y1 prime is still exponential x. Y prime is still exponential x. Yeah, exponential x. Good. So that's it. All right. Next, what of y2? Exponential 2x. If I differentiate exponential 2x, what will I be having?
2 exponential 2x.
Exactly. It will be what 2 exponential 2, and you just use that trick for exponential function. Next, if I differentiate this one again, what do I have? It will be 4
Or
exponential 2x. Do you
exponential.
understand that?
Yes, yes.
Exactly. Next, let's go. Y3 now is exponential 3x. This one what 3
That will be 9 exponential
then
3x.
exponential 3x. So this is I want to get what the determinant. Okay. So what do we now do? Well, if you find this determinant, like if you find this determinant and just okay, you want
Plus
to
minus plus.
like you want to like expand those determinant and see. You observe that this determinant here is not 0. This determinant here is not what? Is not 0. Yeah, determinant here is not 0. It did not even follow the pattern of making. Okay, let me even tell you when to know that a determinant is 0. You see, number one, look at this type of determinant. Number one, it's one for whether 2 by 2 or 3 by 3, but I'll be using 2 by 2 to explain. Number one is that check if any row or any column is the same thing, then the determinant is 0. Look at this column now, 2, 4, 2, 4. The same thing, the determinant is 0. For example, look at this one. See, 2, 3, 4. Let me say I still have 2, 3, 4 here. And I have like 0 minus 1, 7. For this row that is here to be the same, you can go and verify it yourself. This determinant to be 0. For this column to be the same, this determinant is 0. That's number one. Number two is that if any row or any column are in proportion to each other, that is, check. For example, now, let me say I'm having 2, 3, 4. Now, give me any number.
4.
A number 4, good. Use that 4 to multiply everything you have. You'll be having 8, 12, 16. Aha. Let me say I don't have anything like 0, minus 3, 0. You see what you have here? This determinant to be 0. This determinant to be 0. You can test it if you want to test it. It will work. This determinant is 0. Why? This row and this row, they are like proportion to that. You observe that if I use 4 to multiply all this, it will give me everything here. Then so these two rows, the two rows are in proportion. Therefore, the determinant is equal to 0. The two rows are ahead. So none of them happened here. Therefore, they are not what? None of them happened in this one. Therefore, the determinant is not 0. The determinant is not what? Is not 0. Yeah, the determinant is not 0.
Independent.
Yes. Are we together?
Yes, we are together.
Nice. So that's it. Now, the last thing we are going to be looking at is like type of solution that you can obtain while solving a differential equation. Type of solution that you can. Thank God we have done some differential equation before in the past like that. So type of solution that you can obtain in a different. Let me put it in another page. Type of solution that you can obtain. That is solutions of differential equations. Solution of differential equation. What are those solutions that you see? We have different type of solution. Number one, we have what we call general solution. We have what we call general solution. We have what we call particular solution. We have what we call what? Particular solution. Are we together?
Yes.
Good. I'm coming. Yeah, we have general solution. We have what? Particular solution. Also, we have what we call a complete solution. Well, we have what we call, okay, let me say we have what we call singular solution. And we have what we call a complete solution. A complete solution. Yes. You see, all these are what we call, all these are the type of solution we are going to be meeting in a differential equation. But the thing is that I don't just like to be defining all this without us solving the question. So in our next class, we are going to be solving differential equations only. We are going to be solving differential equations only. Yes, we are going to solve differential equations only. So when we are meeting those solutions, I'll be telling that, oh, these are the type of solution. But your assignment is that you have to define these solutions for me. Define these solutions for me. So in our next class, your definition, I'll be using it to you. You'll be observing it with the solution you observe. Like I'll be telling you, like after you have understood definition of all this, when we are solving questions, I'll be showing that, okay, this is an example of a general solution. You can see the solution that contain arbitrary constant. Oh, this is a general solution, and so on like that. So from beginning of today's class, we observe difference between ODE and PDE, how to check order and degree. We learned that, how to check order and degree. Next is that we learned how to check if an equation is linear or homogeneous. And also we learned about linear dependence using the Wronskian method. And then lastly, solutions to differential equation. Which are general, particular, singular, and common. So just define them. They will meet in our next class. Any question?
No, not. There's no question.
Okay, now. So make sure you do that stuff. I'll send the note to you in some seconds now.
All right. Thank you so much.
Oh yeah, no, while you're welcome. Okay, bye.
All right. Thank you so much. Good night. Assalamu alaikum.
Wa alaikum salam.